Hi, I'm Will Drury. In this video, we'll be discussing ideas we have for creating an open operating system that aims to be secure by default. Chromium OS is driven by the fact that all apps are web apps. And because of that, we get a lot of interesting security features that we can take advantage of. Web apps are already protected from each other. It's just how the internet works. Every web app is on a domain, and each domain can't access each other without jumping through some crazy hoops. And so we want that kind of default security, and we get that for free from the internet. Now, below that, we want to make sure that things that go wrong when web apps do bad things, that we keep them isolated from the system. And we do that with a sandbox. So we make sure that all the code that's running that accesses that external data, that runs isolated from the rest of the system. And we cheroot that, and we make sure it runs in its own process namespace. But it's kind of not enough. That just stops one part. We want to do it to the whole system. So we step up a level, and we cover what the browser needs. So we see, does the browser need to access this? Does the browser need to access that? If it does, we give it access, but that's it. We limit it there. And we do that using the same approach. We use process name spacing, but we apply a bunch of other things. We limit the capabilities. We put it in secure no root jail, so there's no way that it can ever access super user privileges. And then as we move up or further down into the system, there's system services, and we want those isolated the same way. And so we can use those same tricks, but we can also apply a kind of a globally aggressive mandatory access control scheme. Normally, you can only do that in a very pointed fashion. You can apply it to one program or another program because you know how they work. But when you download something new, it doesn't work. And so we get around that. All the things we have are known in advance, and we can secure them appropriately. Everything else is a web app. Below the system services and below the browser, it's where all the files are, all the files that run the browser, all the files that run those services, and all the configuration data. And so we keep all the root file system data, all the system information on one partition. And then all your data is kept encrypted on another partition. And that means it makes it really easy for us to do system updates. If we want to pull down some extra information, we can just pull it down, we can apply it, and then reboot, and you're good. What's interesting, though, is that we use multiple partitions for this. We keep a system partition, and we keep a second system partition. And when we download an update, we check to make sure that update's authentic, and then we check what happened on the original partition, and then just update the other partition. And when everything's done, then we flip the switch, and you're ready to go. But if you interrupt it along the way, that's not a problem. It should be okay. Even though we check the signature on the auto update to make sure no one's tampered with it, we should really be doing more. We need to make sure that the root file system hasn't been changed since the last time we updated it. We want to make sure that all the software we've installed is exactly as it should be. To do that, we look at the file system at a block level, and each block is then hashed, and that cryptographic hash is stored in a big binary blob at the end of the file system. That blob is then checked by the kernel during boot to make sure that nothing has changed on the file system. Checking the file system isn't enough, though. We have to make sure the kernel hasn't been changed. To do that, we can check it with the firmware. We have custom firmware that gives us that really fast boot speed. It also gives a small read-only segment, and in that read-only segment, we can store public key, and we can store useful secure recovery data. That key can then check anything that comes after it in the boot path, and so we can make sure that any changeable firmware is up to date and as we expect, and that the kernel is okay. We know there are going to be bugs. We can't stop everything, but we can make sure that if something does happen, you can reboot and you'll be safe. So the secure recovery code is triggered by the verified boot process. If something's wrong and you need to clean your system up, you can boot right into it, plug a USB stick in, and then you'll know your system is in a known good state. That concludes our overview of what we have in mind. We know it's not perfect, and there's a lot of room to innovate, and we'd like your help. If you're a developer, put your notebook in developer mode and come on over to chromium.org.